So, and we've basically been spending most of our time in chapter 16 not talking about the easy stuff. I'm not talking about the easy stuff because it's easy, not because it's not important. I expect you to be able to get some of the things that are in the study guide that we haven't talked about on your own. What we've spent our time doing since Friday is talking about how to do chemistry with carboxylic acid. So we talked about the Fischer esterification. We talked about hydrolysis of esters under acidic conditions. And then we also talked about starting with carboxylic acids, converting them to other things, but through important intermediates. So the classic example of that was convert the carboxylic acid into an acid chloride using SOCl2. Once you do that, you can do any of the things your text tells you can do with acid chlorides. And we're not going to spend any time at all on that because that chemistry is easy. Nucleophile attacks, get a tetrahedral intermediate, then the leaving group leaves, and you're good to go. We also then talked about another strategy that's very important, and that is use of a coupling reagent to make amide bonds. So we introduced this reagent DCC, dicyclohexyl carbodiimide, which will take an amine as your nucleophile and a carboxylic acid. Here's the carbonyl carbon, there's the carbonyl oxygen, and there's the OH group. And remember, the classic problem with carboxylic acids is what are you going to do with that acidic proton? So DCC actually removes the acidic proton first, then the carboxylate nucleophile attacks the blue carbon, which should look weird to you, but which should sort of resemble a carbonyl carbon. Look at those carbon-nitrogen pi bonds. It's kind of like an imine on both sides. We attack the carbonyl carbon, and electrons move out onto the positively charged nitrogen. Then the nucleophile, the amine, can now attack the carbonyl carbon without deprotonating the carboxylic acid. That gives you this tetrahedral intermediate, and then there was a ton of things going on there. So let's just talk through them once more, because I remember it was just at the very end of lecture that we sort of flew through that. In blue is what used to be the carbonyl carbon. In pink is the negatively charged oxygen of the tetrahedral intermediate. In purple is the amine nucleophile, and in orange is this thing which used to be DCC, but which is gradually morphing into a good leaving group. Now, notice that the nucleophile is positively charged. If we want it to stay, we need to get rid of one of those protons. And what happens is that the negatively charged oxygen kicks down and kicks off the leaving group. At the same time, so these two arrows are familiar. You've seen those before a ton of times. They're not new. They're not even interesting. It's the kicker offer kicks off the leaving group. What remains then is what happens to the leaving group as it's leaving. And basically, as it's leaving, it picks off this proton from the amine nucleophile, allowing it to stay. So electrons kick down to form an oxygen-carbon pi bond. Carbon-nitrogen pi bond breaks, and lone pairs on the nitrogen pick up the proton as it leaves. This is an intramolecular process, and that is why I have the numbers 1 through 6 there. Some of you have asked before, when can reactions be intramolecular? And the answer is usually when they can proceed through ring sizes that are reasonable. Think 5 or 6 rings. 5 or 6 atoms in a ring. So notice there are 6 atoms. It doesn't look like they're in a ring, but all we mean by numbering 1 through 6 is that if you made a model of this compound, it would be really easy for this nitrogen at position 6 to reach the proton that's at position 1 and remove it. You can build, if you've ever played around with the model set, if you try to do this kind of thing with atoms that are 4 atoms apart, it doesn't quite make the cut. The nitrogen can't quite get to the proton. Okay. So that's how we get the amide bond, and the leaving group that leaves is this dicyclohexylurea. Notice that now it's a neutral leaving group. If it hadn't picked up the proton from the amide nitrogen as it was leaving, it would leave as negatively charged. Now it's very neutral, very stable, and very easy to separate from your desired molecule. And that's how we made this amide bond. So the functional group that we just made, which I'll highlight in blue, is now called an amide. So that's a direct way of making an amide bond. We sidestep the acid chloride by using a coupling reagent that can take care of the acidic proton and be a good leaving group at the same time. All right, are there questions about that DCC reaction? Go ahead.
Can you remind me what the molecules or compounds are on the right side in orange?
Molecules on the right side in orange, that's a leaving group. This is the DCC portion. It's called dicyclohexylurea. That's not important.
Is that CY?
CY, sorry. CY stands for cyclohexyl. So here is the key. Squiggly line means everything else it's connected to, just the cyclohexane ring. Yep, good. What else? Yeah.
The NH2 can attack the carbonyl carbon because of the leaving group.
Why can the NH2 attack the carbonyl carbon here? Because of how reactive the leaving group is, yeah. Now you could ask, do I need a base to remove the proton from the NH2 before it attacks? It's a good question. I'm mostly just following the mechanism that's in the text here. I noticed that I pointed out at the beginning that when actual chemists do this reaction, they include a non-nucleophilic base, and part of its purpose may be to deprotonate this nitrogen as it's attacking. What else? Yeah? Do you need to be able to replicate it with arrow pushing? I do want you to know the mechanism. Nevertheless, understand on a multiple choice exam, like the one you'll be taking starting Thursday, you won't necessarily be drawing any mechanisms for me. Instead, you'll be choosing among options, where one way to ask the question is to have all of the options wrong except one. The other is to have all of them right except one, or which of the following makes sense. Anyway, yeah. So I do want you to be able to work your way through this mechanism as it's listed in the textbook. Okay. So that's DCC. Now, I think with that we have dealt with most of the reactions that carboxylic acids do. What I want to do now is spend just a little bit of time on amides, though you'll understand why we're not going to spend a ton of time on amides in just a second. So here is the structure of an amide. Recall that I've said that amides are very stable. They are at the bottom of our list of reactivity for carbonyl compounds. Remember, we had aldehydes, ketones, acid chlorides, and a couple other things which we'll talk about later today at the top of the list. Then we had esters and thioesters sort of in the middle of the list. And then amides were sort of at the bottom. Below that was the carboxylate, which is not even an electrophile. The amide is very stable for a couple of reasons. First, the RNH minus is not a good leaving group. Second, nitrogens are good electron donating groups via resonance, and the lone pair on the amide nitrogen can donate electron density into the carbonyl carbon. If you like, we can draw that resonance structure really quickly. This is that resonance structure that I'm talking about. And to the extent that that amide nitrogen can donate electron density into a pi bond with the carbonyl carbon, that makes the carbonyl carbon less electron poor. Less electron poor means less electrophilic, less reactive. Amides are very stable, and this is a good thing because the workhorses of biology for doing chemistry and a lot of structural protein molecules are connected by amide bonds. And so you actually have to have enzymes to catalyze the breaking of amide bonds because they're very, very stable, and amide bond breaking is really, really slow. Nevertheless, there's a couple of reactions shown in your text that allow you to do this. I'm reluctant to talk about these because they don't work really well. People generally don't go to the lab and do this, in part because you have to really, really push the reaction to make it work. So your text points out that under strongly basic acidic conditions, that didn't make any sense. I meant aqueous. Strongly basic aqueous conditions, you can do amide hydrolysis, which will replace which will allow OH minus to be the nucleophile, and which will replace the NHR group of the amide with OH of the hydroxide, and ultimately give you as products the carboxylate and the amine. I'll show you this mechanism, but I'll point out that you really have to cook it. So here's our fire triangle. Because amides are very stable, this reaction ends up being thermodynamically favorable, but it's really, really slow because amides are not that electrophilic. The mechanism has, as you would expect, negatively charged oxygen attack the carbonyl carbon to give you a tetrahedral intermediate. And this step here is going to illustrate why I don't really like spending a lot of time on this reaction. Because if we looked at this tetrahedral intermediate, as I've trained you to do, OH minus was the nucleophile, NHR is the potential leaving group. If you looked at that tetrahedral intermediate and said, which is going to leave, OH minus or NHR minus? Based on pKa's, you would OH minus, absolutely, right? Because OH minus is much less basic than NHR minus. You can figure that out from a pKa table. So you would expect this first step to go backwards most of the time. But we're going to make the argument, as we did for ester saponification, that for the amide, if we do kick off the NHR minus, suddenly we've generated a carboxylic acid. And so as that NHR minus is leaving, it can pick up the proton from the carboxylic acid and give us the neutral amine and the carboxylate. So that's how you push arrows through that. It's not really that hard. You can do it, but again, don't go to Professor Castle and say, dude, I really want to hydrolyze an amide, because he's going to tell you, why would you do that? You would just, if you want the carboxylic acid, just buy the carboxylic acid, right? We'll come back to a little bit later, probably next time, one of the ways that nature, probably you'll wait till biochemistry to learn how nature hydrolyzes amides. It's related to having a group here that can hydrogen bond with the carbonyl carbon and stabilize the tetrahedral intermediate. It's also related to how you handle this nucleophile. And you'll learn more about that when in biochemistry you learn about serine proteases. I want to just show briefly that you can do this amide hydrolysis reaction also under strongly acidic aqueous conditions. And in that case, your product is the carboxylate and then the corresponding, not amine, but ammonium. Why is it ammonium instead of amine? Well, just look at the conditions. The pH is really, really low, and at low pH, amines are protonated. The mechanism here, I'm not going to draw for you. It is analogous, and your text doesn't draw it either, but it's analogous to acid-catalyzed ester hydrolysis. In other words, you would first protonate the carbonyl oxygen, then have water attack, and you would use proton transfer to trade who was the good leaving group, and ultimately a neutral oxygen would kick off an amino group as the leaving group. Okay, amide hydrolysis under acidic or basic conditions. Again, not a fantastic reaction, but one that your text mentions, and so I thought we would talk about it. Sure, yeah, okay. Questions about that? Just thinking about what else. All right, let's do some biology. So we're going to spend the rest of the time today and a lot of time next time talking about examples of these kinds of reactions, which are nucleophilic acyl substitution reactions in biology. A lot of this stuff is in your text. Every time I talk about this stuff, it generates anxiety on the part of students who want to know What exactly about this should I know? To facilitate our discussion, To facilitate our discussion, I'm going to copy and paste some things because I don't want to spend all of our time together drawing. I recognize that you can get a lot of the things that we'll talk about in the notes if you can't draw them. So today's story picks up with the idea of amide bonds, and it's related to what I just told you, which is amide bonds are very stable. Okay? So you often need enzymes to deal with them. Now, certain kinds of bacteria have very rigid cell walls. They're sort of coated with something called peptidoglycan, which is a mixture of carbohydrates and amino acids. It's the sugar coating of various bacteria and allows them to survive in a lot of different situations. This is a close-up of one portion of the bacterial peptidoglycan cell wall. And the goal in bacterial cell wall synthesis is nature needs to take two such molecules, and it needs to basically, I haven't shown you what's on this arm, but there's a nucleophile at the end of it. And nature needs to take the nucleophile, maybe which I'll highlight in purple at the end of this, and have it attack this amide bond in red on another molecule. So this is a polymerization or a cross-linking reaction. You need to take one peptidoglycan and link it to another. I used to show students this, but it scared them, and I realized the juice wasn't worth the squeeze. So if you want to know more, I got like a ton of slides on it that we could talk about, but it's not necessary for our discussion today. Understand, though, that the first step of this reaction is that nature needs to hydrolyze this amide bond and convert it to an ester. And the ester is going to be linked to an enzyme. So here is the enzyme, glycopeptide transpeptidase. I'm drawing it as Pac-Man. That's way before your time, so Google it up and read the Wikipedia article. Pac-Man was very big back in the day. And anyway, the enzyme doesn't actually look like this, but this communicates that you've got a lot of parts of the enzyme and then a portion that matters, which is the enzyme active site. In that enzyme active site, you have a hydroxyl group and a base. And the base deprotonates the hydroxyl group to make it nucleophilic, and I drew it so these would sort of look like teeth, all right? And what we want to have happen here is for the negatively charged oxygen on the enzyme to attack the carbonyl carbon of the amide to generate a tetrahedral intermediate. And then maybe with proton transfer, we want to clip off this section, have it leave as a leaving group. And that's going to generate a molecule where all of this is bonded to the oxygen of the enzyme through an ester bond with this carbon. Okay? You don't have to imagine that, just the idea that we're going to break this amide apart. The enzyme has the ability to do this, and we want to connect this carbonyl carbon of this amide bond with this oxygen. And then the other things can happen. And if you want to know more about that, please come talk to me. I'm happy to talk about it. It's kind of cool, and it allows me to show you very interesting and large structures, and it's kind of an OChem flex that makes me feel good about myself, so please. Now, where do you come into the story? How many of you have ever taken penicillin or amoxicillin before, or some kind of antibiotic? I'm sorry, does HEPA prevent you from disclosing your health history to all of the members of the class? I'm sorry. If you've taken an antibiotic, a penicillin-based antibiotic before, its basic structure is this. So I'm going to draw for you amoxicillin. Some of you hope to prescribe this to sick people at some point in your future. So when drawing amoxicillin, you start with a square that looks like this, and then you put a pentagon here, and then you need two methyl groups here, and for amoxicillin, you've got a side chain here that's a carboxylate group. Notice that one key feature of amoxicillin is an amide bond. That's important. Second, there's another side chain that branches off here. This can be a lot of things depending on what kind of penicillin it is. I'll draw for you what it is in the case of amoxicillin. You've got an ammonium group here, a benzene ring here, and an OH group there. That's amoxicillin. And amoxicillin is one of a class of antibiotics that are called beta-lactam antibiotics. So, what does a lactam mean? A lactam just means a cyclic amide. That is an amide or a ring in which one of the bonds in the ring is an amide bond. So that's just a general term. Lactam is a cyclic amide. Beta refers to the fact that the nitrogen that is making the amide with the carbonyl carbon is itself attached to the beta carbon of the ring. So a beta-lactam is, by definition, a four-membered ring. Now, one of the things you know about four-membered rings is they are highly strained. Think of it this way. The ideal bond angle in a four-membered ring is 90 degrees, because squares. You can relax that requirement a little bit through ring puckering, which you learned about in 351, but even then, you can't relieve the angle strain. The ideal bond angle for an amide, an sp2 hybridized carbon, is 120. So you're quite far away from that. And even for these sp3 hybridized carbons, the ideal bond angle there is 109. So we're quite away. The constraints of the ring get us to a point where we can't adopt the ideal bond angles, and that packs in what's called strain, meaning it should be easier to hydrolyze this amide than it is for your conventional run-of-the-mill amide. That's the genius of this antibiotic. So it's a spring-loaded, highly strained amide. It's shelf-stable. You got to put it in the fridge. If you've ever, I don't know, back when you were a kid and you had an ear infection, the doctor probably prescribed this compounded mixture of amoxicillin in some pink. I don't think it's actually pink. The pink was for fun, right? And then they put in some bubblegum flavoring. You were like, yay, medicine, it's great. You put it in the fridge for stability, probably among other reasons, because you don't want to prematurely hydrolyze the amide bond. But let's show you what happens. The genius of the antibiotic here, as I said, is first, the highly strained amide that's even way more reactive than the regular amide of the bacterial peptidoglycan, right? Do you see how this is not part of a ring? There's no ring strain there. Here there is. Now the second part, the second thing that makes this a genius antibiotic is not obvious, and that is this fits into the active site just as well as this portion of the molecule does. Now that's not obvious by looking at the structures. But it turns out that as far as the enzyme is concerned, it can just as easily wrap itself around the antibiotic as it does the bacterial cell wall peptidoglycan. So what I'll show you now is just from your text. And really, it's just nucleophilic acyl substitution. The relevant amino acid from the negatively charged oxygen from the enzyme active site is going to be brought close to the carbonyl carbon of the amide. You're going to get a tetrahedral intermediate. And are we going to draw it all? Yes, we are. Let me show you how to abbreviate in such cases. We're going to use R groups and other things generously, but we're going to draw the key four-membered ring. Here's the negatively charged oxygen. Here's the oxygen from the enzyme. If it's okay, we're going to draw the baby enzyme like that now. It didn't shrink, we're just sort of zooming out. All right, and then I like pentagons, so we'll draw the, nope, that's not a pentagon. That is. And then for fun, we'll just put R there, and I think that does it. Yeah? Okay, so there's our tetrahedral intermediate. Notice that the enzyme also has a group with a proton on it. Now the negatively charged oxygen is going to kick down. The nitrogen's going to leave. As it's leaving, it's going to pick up that proton from the enzyme. And remember, this is going to be fast because it is going to relieve ring strain. And you're going to see when I draw the product, it's now no longer cyclic. At least it no longer has that four-membered ring. So here's the ester. There's the nitrogen. There's the sulfur, there's the pentagon, there's this carboxylate, and then, am I missing something? Ooh, that's ugly. I got it totally wrong. All right, there's the R group. There's the nitrogen, there's the sulfur. Sorry, I'm hearing all the rattling of paper out there as I blithely erase things and redraw, and you guys are scribbling stuff out and tossing papers. And sorry about that. Okay, I think that's everything. Yeah, so notice that now we no longer have that strained system. And also look what we have done to the enzyme. The enzyme needs that free OH group, which got converted into the OH minus here as a nucleophile. Now it's tied up as an ester. This is, what we would say, and we could call this the esterified enzyme because we put an ester on the active site. Oxygen, that active site oxygen is no longer available to do what it's supposed to do. So this is now an inactivated enzyme. That's going to lead to incomplete bacterial cell wall synthesis, which is going to lead to weaker bacterial cell walls. They're going to be less able to adapt to environments, and ultimately this is meant to be the Jolly Roger, but it also looks like General Grievous, which I'm okay with. General Kenobi. So uncivilized. The enzyme is dead. And that stops the bacteria from growing. Okay? So this is actually used a number of times. The strategy of inactivating an enzyme by modifying or acylating a key functional group in the enzyme active site is used all over the place in biochemistry. Now, unfortunately, we don't have the last word on this, and that is because bacteria have evolved a way of dealing with this. And what do? They have an enzyme that's called beta-lactamase. And if you've ever worked in a molecular biology lab, you know that you can sometimes selectively grow up one strain of bacteria over another by growing them up under antibiotic conditions, and you give the bacteria you want a plasmid that encodes this enzyme, beta-lactamase, so they can survive the amoxicillin, but other undesired bacteria can't. Well, bacteria are pretty good at trading around plasmids, and there are a number of bacteria that are now resistant to penicillin or beta-lactam antibiotics. All they do is that enzyme gets in there and it hydrolyzes the beta-lactam before it can get into the active site of your glycopeptide transpeptidase. So that's the beta-lactam antibiotic story. And it's a classic example of amide stability and also nucleophilic acyl substitution. Because notice what happens. Nucleophile attacks, tetrahedral intermediate, leaving group leaves. Okay, questions about that story? I'll ask one. Do I have to have memorized the structure of amoxicillin? Do you want to? No? Okay, then no. Yeah, go ahead.
What would be like the main takeaway,
What would be the main takeaway hypothetically? Hypothetically on an exam. What is the test question? Well, check out the text, which actually does ask you some questions on this subject. I could ask you why is it possible to hydrolyze the beta-lactam? You could talk about ring strain. We could talk about mechanism. I could ask which arrows are reasonable versus not. All right, what else? Yes?
To go back up to the
Yeah.
Looking at it, that would, if I'm understanding right, that was all. How does bacteria get to that?
Right, good question. And the question is, this would also make an ester. It turns out the ester that results from this process gets intercepted by a nucleophile from somewhere else, and you end up with an amide bond that's more stable. It's a good question as to why that's not overcomable here, and I don't have a great answer for you. Yeah. It could have to do with differences in shape. If I'm hand waving an answer, it's probably related to the differences in shape between the beta-lactam and all of this. Okay, others? Okay, so as we've been talking, you've seen that, for example, acid chlorides are highly versatile intermediates because you can take them and you can make esters, you can make anhydrides, you could make thioesters, you could make carboxylic acids, you could make amides. And so you might be thinking, great, biology has its reagent, right? Acid chlorides are awesome. Turns out they're too reactive and they're not very stable in aqueous conditions. So it's not a great choice. So nature has some other options and we want to talk about them. The leaving groups are going to be somewhat unfamiliar here unless you can think back to what we talked about in our chapter 15 where we introduced acids that contain phosphorus. So we're going to talk about nature's alternatives to acid chlorides, and these are molecules which we're broadly going to call acyl phosphates. Acyl is what we mean for an R group attached to a carbonyl carbon with an oxygen, and then something else on the other side. So an acyl phosphate has this basic structure. This is a very simple acyl phosphate. And here is another which you won't like. It also has the phosphorus, but instead of having two negatively charged oxygens, this acyl phosphate is going to be attached to the 5' end of a ribose ring. And if that doesn't sound familiar, don't worry about it. We'll get back to nucleic acids a little bit later this semester. Probably you've seen adenosine before, or at least have heard that word. And this is called an acyl, what we're going to call an acyl AMP, and AMP stands for adenosine monophosphate. But the basic idea here is that what I'm going to highlight in orange is a Y group from our original discussion of carbonyl chemistry, or rather a potential leaving group. And here with the AMP, it's even bigger. Whoa, looks like I'm making a sick snowman that's out of yellow snow? Where did the, okay. Sometimes the color scheme works against us. So all of this is the good leaving group. So you can see how, I mean, let's first talk about what the good leaving group is going to be. Maybe I'll shift these over here. If a nucleophile were to come in and attack, and a leaving group left, you would get a tetrahedral intermediate that looked like this. And then your product would be, there's the nucleophile, and the leaving group would be this. Now, as we've learned about pKa's, probably that would need to leave. Remember, the last pKa of phosphoric acid is around 12. So probably this would leave as the dianion instead of the trianion. Probably there would be a proton transfer that would happen either as the leaving group is leaving or before. Your text glosses over that entirely, and we're also not going to worry about it. But this is a classic example of what we've started calling a nucleophilic acyl substitution reaction. because we substitute a nucleophile for the leaving group. And similarly, we can do exactly the same thing here with the AMP, with the acyl AMP. Your nucleophile would attack the carbonyl carbon. You would get the familiar tetrahedral intermediate, which I am going to just abbreviate shamelessly as this. And then electrons would kick down and the leaving group would leave. And that would give you your acyl substitution product. And then that would give you your leaving group, which would be AMP. And again, thinking about what we learned about for pKa's of acids containing phosphorus, the pKa of the monoanion is around 7, so it's a toss-up at physiological pH whether you should expect the monoanion there or the dianion. And your text glosses over that, and so will we. But the idea is, again, nucleophile replaces leaving group. If you look at these acyl phosphates, the thing that makes them reactive is, first, the presence of a good leaving group. And second, if you look at them, they sort of resemble anhydrides. The only difference between the acyl phosphate and an anhydride is what's on the other side of the oxygen there in the middle is a phosphorus instead of a carbon. So you should expect acyl phosphates to be about as reactive as anhydrides, only they're just more stable under aqueous conditions in biology. All right, questions about that so far? Yeah.
So the acyl phosphates are similar to anhydrides, but they're used for replacement for acid chlorides?
They're used as replacements in biology for acid chlorides or anhydrides, and that is because they are water stable at least for a short amount of time. Yeah. Others? Yeah.
Will magnesium ion act as a cofactor?
So in a lot of these reactions, magnesium will act as a cofactor, and I'll show you that. In many cases, magnesium helps. One of the reasons your text glosses over what the leaving group is because magnesium will act as a counter ion to sort of neutralize the negative charges on some of these leaving groups to help them leave. And I'll give you an example of that. And actually, I want to show you how nature makes some of these acyl phosphates. This is in your text. You'll get it in biochemistry, but you probably won't get all the mechanistic details, and so that's the job of the organic chemists to show you. So let's do synthesis of an acyl phosphate. This is always enzyme catalyzed, and we're not going to show you what the structure of the enzyme is. Magnesium is often a cofactor. Acyl phosphate synthesis takes advantage of the key property of carboxylic acids, which is that they are carboxylates at physiological pH, and we're going to use them as nucleophiles. The reactive partner is ATP, adenosine triphosphate. So, if you've buckled up and took your vitamins like President Nelson suggested, get ready to draw this large molecule. Come on, it's not that bad. So this is the triphosphate part of ATP. We biochemists have these describe these three phosphates differently. This one is the closest to the adenosine ring, so it's called alpha. This one is next, and then it's called beta, and this one's called gamma. So you'll hear people in biochem talk about the gamma phosphates in ATP. Then I've already drawn adenosine today, so I'm not going to draw the adenine base on the ribose ring. We could do that, but we'll just put A there. Hopefully that's okay. If you look at ATP, again, the functional groups, again, when a phosphate is attached to another phosphate, that should sort of resemble to you an anhydride, where a carbonyl carbon is attached to another carbonyl carbon via an oxygen. You should sort of see the similarity in structure here and here. And in fact, we will call this bond between the two phosphate groups, we will call that, and there's several of them here, we will call this a phosphoanhydride bond. The enzyme is going to catalyze the reaction of the carboxylate onto the gamma phosphate. The oxygen, lone pair oxygens on the carboxylate are going to attack the gamma phosphate group in a manner that's analogous to carbonyl chemistry. And that should sort of make sense because oxygen's more electronegative than phosphorus. You could draw a resonance structure with a negatively charged oxygen and a positively charged phosphorus. So it makes sense that that phosphorus is electron poor. The other thing that you need to know is that the role of magnesium here is probably to facilitate that attack. You may be skeptical thinking, well, hey, that carboxylate's negatively charged, and those phosphates are also negatively charged. So what about charge repulsion? And the answer is the magnesium helps with that a lot. The enzyme active site helps with that. Magnesium probably bonds to or chelates with those negatively charged oxygens. You attack the phosphorus. You get something analogous to a tetrahedral intermediate. I'm going to draw that for you here, though we are going to abbreviate. It's not a tetrahedral intermediate because look at that phosphorus. It's bonded to, count them, 5 oxygens. And then here I'm just going to put AMP for adenosine monophosphate. I'm not drawing the gamma phosphate or the ribose ring or the adenine base. And again, remember that magnesium is going to help us out with this large amount of negative charge. Electrons on the phosphorus are going to kick down and kick off. They're going to break this phosphoanhydride bond. They're going to kick off ADP as a leaving group and make the acyl phosphate. One of the things I want you to get from this is a sense for how easy versus difficult this reaction is to occur. Notice that above we had a phosphoanhydride bond that I highlighted here. That's the bond that we're breaking in the key mechanistic step. The new bond that we made is not quite a phosphoanhydride, but it's sort of a mixed carbon phosphoanhydride. So you would expect it to be, and I'm running out of space there. Oh, almost got it. Oh well, there's an E there trailing off the page. You would expect this to be about the similar instability. The acyl phosphate product should be similar in stability to the ATP starting material. And so if you were to measure the equilibrium constant for this reaction or the delta G, you would see this is not, it's not terribly downhill. It's about just sort of, it's just sort of even. And so it's a very reasonable reaction to do. Okay, questions about that? Yeah. Is it an equilibrium reaction, or the exact thermodynamics of it are probably going to depend on what the starting materials are and what the products are. For now, it's enough just to realize that it's reasonable because you're taking one high energy carbonyl compound and trading it for another. Yeah?
Could you re-explain the role of magnesium in it?
Yeah, what is the role of magnesium? Magnesium has a 2+ charge on it, so it's good for neutralizing negative charges on the phosphate oxygens. Others? Yes?
We said the acyl phosphates were similar replacements for anhydrides or acids.
Yes.
What would be the environments that you would use, like one or the other would be better for?
So you can't use, I'm talking about biology, I'm not talking about synthetic choices. If you were in the lab, it's probably not worth your time or trouble to make acyl phosphates. Why would biology do that? Because acid chlorides and anhydrides aren't that stable in water. But in biology, your solvent is water. Yeah. Okay, others? Yeah.
Like physiologically, if you had not enough magnesium in the body, would this like slow down this reaction?
So would not having enough magnesium slow this down? That makes good sense to me, though I'm not sure if I can predict any physiological consequences for it. So that's a good question, but one I'm not qualified to answer. I think there's probably a lot of other things that happen with magnesium as well, so it's probably complicated. I happen to know that when my wife was pregnant with our fourth son, Adam, who's now 13 and was having a bad day this morning, she ended up having preeclampsia, and one of the things they tried to do to lower her blood pressure was giving her magnesium. She said it made her veins feel like they were on fire, but I know nothing about the biochemistry behind that. So, yeah, go ahead.
In the textbook, I think you mentioned the carboxylate attacking at the alpha.
Right, right. So the question was, in the text, you saw the carboxylate attacking at the alpha phosphate rather than the gamma. You remember the acyl AMP that I told you about? That's what you get when you attack. I'm sorry, that sounded like I was doling out a consequence. That's what you get when you. No, this is ATP. If the carboxylate attacked at the alpha, then the AMP is what you would get. We have just enough time for me to illustrate that, but only via copy and paste. So for those of you who are drawing on paper, does it ever attack at the beta? I'm not sure on that. It's a good question. This is what attack at alpha would look like. So, whoops, that's not what we want. You attack the alpha phosphate. You get that intermediate where the phosphate is bonded to 4 different things, or 5 different things. Now take a look at this really quickly. Here is what I'm going to just abbreviate as adenosine. Here is the carboxylate that's now attached, and then here's the 5th group. Here you have to decide what the best leaving group is. Is it the alcohol on the adenosine side, or is it the phosphate group on the beta side? And it turns out that in this case, all of this, the beta and gamma phosphates, serve as the leaving group. So electrons kick down and that leaving group leaves. And I'll show you that again next time in case you didn't get it. But that's how you get the acyl AMP. All right, we'll stop there. Have a good Monday. I'll see you Wednesday.